Hi, everyone. This is Rick Gordon with Halo Labs. Thank you for attending our webinar today on sizing and counting with the new Aura system. Really happy to be doing this webinar today in collaboration with Bernardo. And just to remind everybody of how this works, so we'll be presenting the webinar for this morning. If you have any questions, you can address your questions in the questions box in your control panel. We will read those questions at the end. We'll try to get to as many questions as we can. If we run out of time, we can follow up with you individually later and answer your questions. So with that, I'd like to introduce Bernardo Cordovez. Bernardo is Halo Labs founder and chief science officer. He leads our application and business development efforts here at Halo Labs. Bernardo received his PhD in mechanical engineering from Cornell University, where he also did his postdoctoral work. Bernardo has a long history of developing a wide range of scientific instruments in the areas of particle detection and analysis, drug delivery devices, microfluidics, nanophotonics, and bioenergy. Thank you very much, Bernardo, and take it away.
Thanks so much, Rick, and hello, everyone. Thank you so much for joining us this morning Pacific time. I hope everybody is well and safe, and I'm very excited to tell you about the latest advancements of the Aura system as pertaining to sizing and counting. So we have a bit of ground to cover, so let's get to it. So I'll briefly review the BMI workflow. Most of you are very familiar operating in the Horizon system about how it works, but I think it's always good to take a quick look. And then I'll get into the meat of the webinar, which is how do we calibrate the Aura? How does it do? How accurate is it sizing beads? We'll go into counting linearity using BMI, and then ultimately into the heart of the webinar, which is how accurate it is counting USP bead count standards, which is a current limitation of the Horizon system, but that the 100% sampling efficiency and great software of the Aura system circumvents. And then we'll conclude. So let's start with a review of the BMI workflow, which most of you are familiar with. And it's basically 3 simple steps. You background a plate, you load your sample and filter it, and then you measure it. And then you get particle size distributions in as quickly as 1 minute per run. And that includes both backgrounding and measuring. So we start by backgrounding, right, which essentially you load your plate into the Aura system, and then it takes a picture of the raw membrane before particles have been filtered in it. Then you bring your plate into the vacuum manifold and you pipette. Then you'll apply a vacuum. You'll pipette 50 microliters of sample. You will then apply a vacuum, and the sample and particles will basically filter through. And we use a 400 nanometer polycarbonate membrane, so particles larger than 400 nanometers will stay behind. And what it'll result once we reinsert it and re-image it again, we'll have an image that is the combination of the membrane texture plus the particles that have just been filtered. But because we have the reference membrane image, we can then do very accurate pixel by pixel subtraction and inaccurate particle detection. So particles that would be completely impossible to perceive, essentially, without this background now become visible as a result of this highly accurate registration and great detection algorithm that BMI enables. So what this ultimately allows you to do better than any other subvisible particle system out there is the ability to get the 3 tiers of information that are so important to characterize your particle populations. The first one is at the individual particle level. So the system produces size, shape, morphology, and intensity parameters for an individual particle. So for example, this particular particle has an equivalent circular diameter of 57 microns. The next level up is your sample. So for a given well, you're going to get a particle size distribution. Typically in protein biologic formulations, you'll have lots of small particles, certainly sub 10, and then exponentially decaying as the particles become larger. but it's put together in a way that you can play with all of the different morphology and intensity and sizing parameters out there so that you can really characterize what's going on at the single sample level. But the system is high throughput in nature. And what this allows you to do is to essentially, our great software puts together all of the data from all of the different wells, and you can obtain high level insights for the broader particle population. So in this case, for example, there's 40,000 particles of ETFE, the plastic protein mimic from NIST, and the controls hold. And we can do that very, very quickly, at most 1.5 hours for an entire 96 plate run, which is 10 to 20 times faster than the other systems, and there's no washing necessary and none of the problems with dealing with the fluidics. But there's even other advantages. So when we size with background and membrane imaging, inherent to BMI is high refractive index detection, right? And the first step that we do is we first check to make sure that our systems are properly calibrated, and for that we use an ASTM reference calibration slide. So we make sure that our optical components are aligned. We use an ASTM microscope reference calibration slide to characterize an individual system's digital resolution. And then after that, we apply signal processing and algorithms to make sure that we accurately detect the particle sizes. And as you can see in this slide, here's a dot progression on an ASTM reference slide. And we have dots in the reference slide ranging from 3.5 microns to 40 microns. And the actual measured diameters result in the tooltip. This isn't exactly using, as you know, backgrounding, right? Because we're measuring it directly, but this is just for size calibration. And you can see here, for example, the 4.9 micron dots measure 4.7 micrometers in the tooltip. Your 19.8 micrometer dots, they measure 19.9. And that's essentially like our first stab at the calibration. But then most importantly, this isn't a system for measuring, small features defined in chrome on a glass slide. We really want to make sure that it does a good job measuring real particles. So as related to the particles that everybody uses here, we're typically within 0.5 micron of accuracy. So most bead standards, whether they're count or size standards, are definitely specified to be within 100 nanometers of standard deviation. In our system, we're typically, within 0.5 micron of accuracy. You can see in the case for this 15 micron bead on the left, this particular bead measured 14.9 microns. The 10 micron bead measured 10.2 microns. And the 5 micron bead is essentially dead on. So it's very accurate sizing for some of the most characteristic bead counts and sizing standards that are used and applied in the field. One of the complications, however, and many of you have probably encountered this, is that when you work with beads on membranes, and that's whether it's our system or a Raman system, is that beads during filtration, they tend to roll and clump and basically not specifically aggregate. And there's these very strong van der Waals forces that keep them tied together. And no matter essentially how hard you try, they're going to remain stuck. That is only a characteristic of beads. That really doesn't apply for the real protein samples or even ETFE. But at the same time, beads have been used as the workhorse for count calibration. And that's an obstacle for the Horizon system in terms of the analysis. So let's say that you wanted to count how many particles are there from a count standard standpoint. Your results are going to be conditioned by the fact that this triplet is going to measure 1 particle, a doublet is also 1 particle, and then the singlets are individual particles as well. And this problem is actually exacerbated the larger bead sizes become. So we have 3 different beads of 3 different sizes, 10, 15, and 30 microns. And you have equivalent circular diameter on the y-axis. So let's to orient you through this graph. So let's look at a 10 micron bead. So the singlets, which is the bottom left dot, on average are measuring 10 microns. Once you have a doublet, right, then the equivalent circular diameter of a doublet is more like 14 microns, right? That's essentially the area of what happens if you put 2 10 micron beads together. And you can see that it keeps forming more and more of these clusters, which can even become mega clusters. In the case of the 10 micron beads, you can get up to 8 octuplets, if you will. And as the beads become larger, for example, for these 15 or these 30 micrometer spheres, you can form more than clusters of 8 beads or even 10 or more beads in that case. So that would inherently produce inaccurate counting if you were to measure those counts directly. So how are we going to circumvent that? Because again, those particles have been very well characterized and vetted to measure precisely what the bottle tells you that they measured as specified by USB standards. But let's start first with sizing. So what we're going to do is we're going to select 24 wells of 10 micrometer beads, and this is using the new Aura software particle view. Select. It allows you now to visualize all of these, for example, 24 wells at the same time. You can see all of these different scatter plots for each corresponding to an individual well. We can then collapse all of that data, and in this case, we have, for example, semi-intensity versus diameter. And you can see on the right-hand side all of the individual clusters for the singlets, the doublets, the triplets, and the quadruplets forming. As we know, the beads tend to be circular, so let's see if we can tease just the singlets out. We apply circularity color, and we can see those that yellow cluster corresponds to singlets because we know they're round. And now we can literally drag that selection, hover over it, and we can see that that selection measured 10.22 microns with a standard deviation of 320 nanometers. So very, very accurate. And then we can click on any individual bead in that cluster, and we can observe it in semi, in bright field. We can hover over it, look at it in the tooltip, and then see what the particular diameter for that bead was. So it's a very, very powerful software for just collecting a ton of data and really do a deep dive and average and obtain particle sizing that way. So again, that just shows you how fast it is. As you can imagine, this is on a loop, but we can basically obtain insights from individual wells and essentially combine all of that data again. So let me show you that one more time. We have all of these different clusters. Again, this corresponds to the data of 24 wells. And all of the individual clusters that you see forming discretely are clusters of singlets, doublets, triplets, etc. Again, we're going to color them by circularity. We're going to tease out the round ones, and that's just to show you how good of a job the system does at picking out what truly are the beads. You're going to make that selection again. Let me show you that one more time. And then you're going to see in the tooltip how the average is 10.22 microns plus minus 0.32 microns. So clearly the system does a good job measuring the sizes of the beads, but in addition, beads are high contrast samples inherently, and systems like flow imaging and light obscuration they're basically designed to measure beads well, but when it comes to real samples, they struggle. Key advantage of BMI is the ability to conduct high refractive index contrast measurements. And essentially, we have a much, much higher refractive index contrast because we drain all of the matrix solution and are able to obtain high contrast measurements that way. Let me show you how that plays out in real life. This is images from a paper published by Coriolis, in which BMI is compared to MFI and FlowCam for different kinds of particles. Top left is a MAB, top right is ETFE, and then a fatty acid at the bottom. And you can see that the high contrast particles in the horizon basically pop out a lot more. They're a lot darker. They're much higher fidelity when it comes to measuring these particles for real samples. And that's what really and fundamentally matters. And not only that, but we can do that 10 times faster. And one key, and I've touched on this before, but particularly when you compare to flow imaging, it's inherently low refractive index measurement because you're measuring the particles in a liquid. But then in addition, right, because they tend to use higher magnification objectives for some purposes, then the numerical aperture essentially compromises your depth of focus. it's just physics. It's the way it works. And essentially what that means is that for some of the most common optical configurations, you're only going to sample 55 microns out of a 300 micron flow cell, which is a default effectively. So that's about 20% sampling at that point in time. So that's just one of the many limitations. There's over a dozen limitations, or I should say advantages of BMI overflow imaging. From the fact that all of your particles are in focus, that we sample 100% of the samples, the fact that it's fluidics free, that there's no washing needed, that you don't have to worry about fouling, that it's 10 times faster, that we can, it doesn't matter how big your particles are. You don't have to worry about, for example, particles over a couple hundred microns, sticking onto the flow cell. It's transferable if you wanted to adopt it to different orthogonal measurements, and as I presented a handful of weeks before, it's amenable to do protein identification, which we're not going to talk about in this webinar, but it's one of the really key attributes and one of the coolest features of our new systems. So going to count linearity, can I trust the system? Basically, for the new system, the 1 pixel per micron digital resolution allows us to accurately measure 1.6 micron beads. We have linearity over 3 million particles per mil for 1.6 micron particle size standards. And this is even achieved at very low volumes. So this isn't the case for human IgG protein aggregate samples that have been created through stress via agitation. And we can see that different concentrations for 5 microliter wells or even 10 microliter wells result in very repeatable and accurate results. And if you compare that to potentially the several mils required by lighthouse creation or the several hundred microliters needed in flow imaging plus all of the washing steps, it's just a huge advantage. But I think the key thing is that Aura enables reliable absolute particle counting, and that's going to be the heart of the webinar as I get to that now. And 100% matters because it allows you to be accurate. It allows you to make sure that all the particles are in focus, all the particles are properly imaged. You don't have to apply any scaling factors, and that's a limitation, honestly, of our original Horizon system. With the Horizon system only samples 63% of the well, forcing you to the system to extrapolate that 37% difference. And while oftentimes it's a good approximation, when it comes to absolute counting, it is not. But now the Aura with the new, by sampling the entire well and some amazing software features that I'll showcase, it allows you to do a very good job for absolute particle counting. So this is a little bit of a busy slide, but I'm going to show you how we conducted an inter-user, inter-bottle, so several vials, and inter-instrument analysis, proving how the Aura does a good job measuring bead count standards, measuring 3,000 particles per mil. So we used 2 sets of bead count standards, 10 micrometer bead count standards measuring 3,000 particles per mil, and 25 micron bead count standards measuring 3,000 particles per mil. Those are the standard USB bottles that everybody has from Thermo Fisher. So we had 3 users, myself and 2 of my colleagues here, and we used 1 plate, and we backgrounded that same plate on 4 different Aura systems. And that's, again, one of the advantages when you guys want to potentially acquire more than 1 Aura, is that you can measure the same sample, the exact same sample on multiple reference instruments. So each one of us had our own bottle. I had my 10 micrometer count standard bottle and my 25 micrometer count standard bottle, and the same for my colleagues. And then each of us pipetted 8 wells for each size at 50 microliters of volume per well. We then filtered it, we blotted it, and then we measured it into 4 different Aura systems. And then we corroborated these measurements by manually counting how many particles appeared in the bright field image, in the bright field difference image, and then using the new software feature called the expression engine to calculate how many beads are there. So it's a very rigorous study. Essentially, here's a plate layout, right? You can see it. It's I'm user 1, and I pipetted 8 wells of 10 micron beads and 8 wells of 25 micron beads. All of the samples are dispensed at 50 microliters, and my user and my colleagues did the same thing. And then we had some air controls just to make sure that everything was running properly. So we did manual counting verification to ensure that the USP bottles were accurate. And most importantly, if you're dispensing 50 microliters of sample, a given well, 30,000 particles per mil, a given well, if you only pipette 50 microliters per sample, there's only going to be about 150 particles per well. And it's normal to question, hey, is that statistically significant? But the short of it is that absolutely, and it was very repeatable across all users. So we took this bright field difference image. We manually counted all of the different beads using a procedure similar to what that image on the left captures. And then we extrapolated, right, from 150 beads per membrane to the entire experiment. So we measured that plate in all of the different systems every time. And essentially, it was dead on. So manual counts verification did prove, in fact, that the USP bottle did have, in fact, 3,000 particles per mil. And the red dash lines are basically your confidence interval of the plus minus 10 particle, plus minus 10% tolerance interval spec'd by the USP standard. That is just one standard deviation. It could be beyond that, but you have a really high probability that your particles are going to be within that tolerance. So in fact, the bottle has what it has, and 150 micrometers per well can be accurately measured using the eye. So we go back to this conundrum, if you will, of the fact that beads will aggregate. So if we just ran a standard particle counting algorithm, we would dramatically undercount these beads, right? Because they've been aggregated. There's triplets, doublets, and I even showed you how you can even get to octuplets, if that's the correct word, for the case of 10 micrometer beads. But here's the advantage. In Aura and in BMI, all of the information for every particle is known and stored. So, for example, that triplet on the left, we know what its area is. It's stored. For that doublet, it's the same thing. So what we can do is just use some simple 4th grade math, which is we're going to sum the area for all of the bead diameter. So the singlets, we're going to add all of the area of the singlets, the doublets, the triplets, etc. And then we're going to divide by the area of a singlet. And if you do that, you should get how many counts and how many beads were actually there on the membrane. And we want to do that using the same algorithm and not create, for example, just a bead counting algorithm, which, while potentially very powerful, it deviates from the original detection and how everybody's using this today. So we don't want to create an algorithm for sizing beads and diverge to how we're counting particles more traditionally. So this is immediately applicable to the algorithms that you're currently using today. But to make sure that we measure it properly, we do apply some very simple filters. So for example, here you can see that things below 9 microns, they can be debris. So we apply a size cutoff, and we're only going to measure particles for the case of 10 micron beads above 9 microns. So we're going to apply a filter, a size cutoff, and we're going to say only look at particles that are greater than 9 micrometers in size. And those are what we're going to consider our bead population. And this also speaks volumes to the fact that these bottles, they're not 100% clean, and that's not a problem for this system. So once we do that, we're going to use the expression engine, which again, it's an incredibly powerful piece of software in the Aura system that uses the fact that all of the information for every particle is known. So we're going to interrogate all of the particles that are greater than 9 microns. We're going to tell it, and we can even do apply Boolean logic. We're going to tell, I want you, for all the particles that are greater than 9 micrometers in size, I want you to sum its area, and it's going to return a value once you do that. So that's incredibly, so not only can we count how many particles meet that criteria, but we can actually produce, this integral, which is quite amazing. So when we go to show experimental report, if we then go to the expressions tab, because we just use the expression engine, for example, for the different users, you can see that there's about 97,000 square microns worth of bead area across the entire experiment, right? So it just calculated the integral of the total area, the sum of the total area for what we consider to be. Now that we have that value, we can basically take those values, right? We have the integral already. Now let's just divide it by the theoretical diameter of a singlet, and we can just bring that into Excel. This is just, solving for a pi d squared over 4, and that tells you that there's about 1,200 beads over the entire experiment per user, but that's over 8 wells, right? So there's 1,200 beads over 8 wells. That's pretty much exactly 150 beads per well. And then if we can transform bead counts to counts per mil, you get to 3,000 particles per mil. So let's go through that again. This is the integral of the total bead area. We just bring it into Excel. We do some 4th grade math. And so the expression engine tells you that there's 1,200 beads total that met the criteria over 8 wells. Over 1 well, that's 150 beads. And then if you can transform it to particles per mil, you're at 3,000 particles per mil. So it's very simple math. The expression engine is not Excel. It does all of the hard calculations for you, but then to do very simple math, you can just take those values and put them in a very simple CSV, which we're even happy to provide for you. So what do the results look like? So again, for this inter-user, inter-bottle, inter-instrument experiment, we confirmed that for the 10 micron beads, we measured, we were very much within the tolerance. We were at about 3,100 particles per mil, while for the 25 micron beads, we were at around 2,850 particles per mil. So we didn't have to do anything different. We're using the exact same algorithm, and we're very much well within the particle specs. So that's essentially it. So the Aura enables reliable and accurate high refractive index measurements. That sizing and counting is accurate. The expression engine allows us to perform accurate particle counting. And this is all done using essentially validated against ASTM reference standards for the original calibration and bead count standards as well. So again, the testing held in inter-user, inter-bottle, inter-instrument, and we're very excited to augment not just on the fluorescence side, but on the validation side, and enable things that simply weren't possible even with the Horizon instrument. So thank you so much for your time, and I'm very excited to get your questions.
Great, thank you, Bernardo. And as a reminder to everybody, if you have a question, you can type it in the questions box in your control panel, and we will take those questions now. So let me start off with a couple questions that we have for Bernardo. The first question is, you showed a couple different size beads. Is there a reason why you would recommend one versus another, 10 versus 25, for example, or should you use both, or are you okay just using one?
Personally, I'd recommend using the 10 micron beads. They're the first cutoff for the USB standards, and they tend to form smaller mega clusters, right? So if I had to pick one bead to use, it would certainly be the 10 micron bead particle count standards. It doesn't mean that it doesn't work for the other ones, but I think that the results become much more easily interpreted and reliable with the 10 micron bead count standard.
Great, thank you. Next question we have is, will this method work on the Horizon system?
That's a good question. So the short of it is no. And the reason for that is that the Horizon system is not powered with the expression engine. And one key reason why that's not happening yet is because the Horizon does not measure 100% sampling efficiency. So let's assume that you were to do this on the Horizon system, right? What would happen is, because you measure 63%, the Horizon measures about 63% of the well area. Beads tend to, as you've seen, they filter and they tend to localize closer to the center of the well. So in essence, the Horizon will sample all of the beads that are present. But then you'll apply a scaling factor of 1.37, and you're going to overestimate the bead concentration that was actually there. Now, that is generally not a problem for real protein formulations where the particles are nicely separated and stuck throughout the membrane, right? So they interrogate the entire area of the membrane. But beads do tend to localize closer to the center, particularly the larger ones, the 10s and the 25s, which are, again, the USB count standards. So if you did this in Horizon, you would overcount. So the short of it is no.
Okay, great, thank you very much. Next question is about the simultaneous display of data from multiple wells. You showed that earlier in the presentation. Is that available on the Horizon software version 2.0?
I will have to.
I don't believe it is.
Yes, I was going to defer to you. So
okay.
No.
Yeah, I don't believe it is. I can double check and get back to everyone on that, but I believe it is not available on that. And then looks like the next question we have is about high concentration samples. Is there any impact on the counts in high concentration samples? I don't know if the beads really address high concentration samples, but I think maybe you can just mention the new application note that we have out on high concentration samples as well.
So exactly, so you just answered that. So yeah, the beads do not answer high concentration samples. The beads, 3,000 particles per mil, if anything, are low concentration standards. We just put out a tech note on how to work with high concentration standards. High concentration, it can mean high protein concentration or high particle concentration. That being said, we have a really nice workflow that allows us to work with very high concentrations, and it involves using membrane washing as a result to remove potentially soluble non-particles from the surface. And I know Rick and us, we will be, if there's interest in that, we'd be happy to share that tech note with you on what is the best way to work with those. But again, generally with protein samples, you don't have to worry about the fact that they will roll and aggregate during filtration. They tend to be high surface area to volume ratio, so that means they'll nicely stick onto the surface. So essentially the measurement, this phenomena of things kind of coming in together and forming doublets, singlets, or that really doesn't happen with real samples.
Great, and I can just add that we've got customers working up 150, 200 mg per ml protein concentrations very successfully on these membranes, so it is not a problem at all. And the tech note does address those methods, which you can find on our website for download. So, okay, great. That's the last of the questions. So if anyone thinks of other questions later, you can email them to sales@halolabs.com or your local representative. And thank you everyone for joining the webinar today.
Thank you.